So yeah, I'm happy to be talking to all of you today. As Jen said, I work at the Flatiron Institute in New York. I'm an associate research scientist at the Center for Computational Astrophysics, and I should always give a little plug that we have not only lots of events and things here, but we're always hiring, or on a yearly basis, we hire grad students to come and visit for the predoctoral scholars program and independent research fellows to do Flatiron Research Fellow postdocs. So if you are excited about some of the things you hear that are happening at CCA and want to come here, I'm always happy to chat about possibilities there. And so without further ado, I'm going to be talking about data-driven methods for achieving extreme precision radial velocities. And normally I would start my talk by trying to give some motivation, but I don't think that I need to convince this crowd here that Earth detection is an important goal for us, and EPRV is the way that we want to do that. So starting from this motivation, we want to be able to find Earth-like planets. Just a reminder that detecting an Earth isn't one simple process. When we say that, we're actually referring to a whole lot of different steps here, which is why it's so important to have these collaboration networks like this so that we can have expertise in all of these areas come together. But in general, when we talk about detecting an Earth-like planet, we're talking about running a survey where we choose a good star to observe, point our telescope at it, send the light through a spectrograph, which has been very carefully engineered and tons of work goes into this step. We get a spectrum on our detector. We then have to extract that spectrum into a 1D spectrum and extract from that down to a radial velocity. Then we redo all of this on some different time scale so that we can build up our time series of radial velocities. And if we did it right and we're lucky in the star, we can end up with a Keplerian signal and indirectly detect the Earth-like planet. Along this path, there's a whole lot of steps, and the stakes are high for getting all of these steps right. It's really challenging. So the spectrograph needs to be extremely well engineered and calibrated down to millikelvin equivalent temperature stability to get the amplitudes, the extreme precision amplitudes that we want. That sort of instrument stability translates to a Doppler shift of a few silicon atoms on the detector. So not just measuring in pixels, but measuring in the actual radius of the atoms that go into each pixel. So this is a really difficult measurement to make. We need to process our data well enough that we can get out a 9 centimeter per second amplitude signal to find an Earth-like planet. And we need to get that kind of precision not just once, but repeatedly over multiple years in order to get the long period Earth-like planets. And so there's a lot of things that we need to do in order to make this whole machinery work right and find the Earth-like planets. And I'm breaking this down in this slide to just a few examples of the many steps that we need to think about along the way. And I'm not going to be talking about all of these things today, but I think that there's some things in common to all of the different variables along the path that we're thinking about. It's hard. It's measuring very precise small quantities, but also we have one thing on our side here, which is that we have a lot of data in hand. The data that we have can be a really powerful weapon, much like Link's Master Sword in new Game of the Year, Legend of Zelda: Tears of the Kingdom, which I'm a little obsessed with and might make its way into this talk. But why do I say that data is a weapon in our arsenal here? We can use the amount of data that we've collected from spectrographs, all of the surveys that have been executed so far, the instrument calibration data, all of these stacks and stacks and stacks of pixels and time series measurements in order to improve the models that we're making. So When I talk about data-driven approaches, really I'm thinking about using data as a choice in building the models. And this applies to many different challenges in the extreme precision radial velocity world. In general, I would say that when you build a model to fit to your data, you can rely more on theory, which would be something like solving something purely from first principles, absolutely minimizing the amount of empirical data that goes in. Or you can tip the scale more towards relying on the data in hand to sort of infer things and allow you to get a model that maybe fits things better than a flawed theory could. And the extreme there is these days, I let ChatGPT do the work, or I made an unsupervised machine learning model. This can obviously be extremely powerful. I would say that the main thing that determines where you fall along this scale between theory-driven and data-driven models is the flexibility of the models, often measured as the number of free parameters that you have here. With data-driven models being more flexible and therefore more able to be influenced by the data to change in response to what we're actually seeing. And the models that we choose are not a dichotomy between theory-driven or data-driven. It's really a continuum. Any model falls somewhere in this range, and most fall somewhere in the middle here. Going towards theory-driven has a lot of benefits, namely that it tends to make things more interpretable and more grounded in physical reality. Although I would say this isn't quite as fundamental to my definition here as the flexibility, because there are examples of things that are flexible but not interpretable, or interpretable but not flexible. And I think that we're trying to find the right balance between these two things. So one of the underlying themes of this talk is going to be about finding the right balance along this continuum. And I argue that the right balance is a little bit more towards the data-driven side than a lot of our long-standing traditional methods of analysis are. So how can we push the scale a little bit towards data-driven without losing the benefits of being grounded in theory and having that interpretability? For the rest of this talk, I'm going to focus on a few different parts of the EPRV mission and talk about work in a few different areas along this, ranging from instrument calibration to modeling extracted time series and improving the extractions and the diagnostics of stellar variability. But all of these things are going to have a common theme of a data-driven approach to it. So I'm going to start with instrument calibration, and specifically wavelength calibration, because it illustrates some important themes here. This is work based on, this is a section based on work that I did with Lily Zhao a couple of years back. And our mission here was to try and improve the wavelength solutions for the EXPRESspectrograph, which Lily is an expert builder and user of. We want to find a wavelength solution here that accurately and precisely describes the mapping from pixel positions on the detector to the wavelengths of light hitting it. This is an extremely fundamental piece of measuring radial velocities. If you get your wavelength solution wrong, your radial velocities will be wrong. And EXPRESS, among other instruments, has a laser frequency comb, which has really opened up a new regime of data, thanks to the extreme concentration and regularity of LFC lines that you can get on your detector. So we started this project really when Lily pointed out that she was looking at the residuals to wavelength solution fits, looking at all of the LFC lines. And the old way of doing things, which relied on doing a 9th degree polynomial fit to the LFC lines, left huge residuals that had a lot of structure to them. And she noticed that actually the structures in these residuals match up to detector non-uniformities. So places where there are like stitching boundaries that cause changes too sharp to be properly fit with a smooth polynomial. This was all suggesting that that the polynomial fit isn't flexible enough to capture what's actually happening in the wavelength solution. And that makes sense. I think we always knew that it was more complicated than a 9th degree polynomial. We were just using that model because it was what we were capable of doing with the data in hand from gas lamps that were used to calibrate before this. But now that we have the LFC, how can we improve the wavelength solution? So the first improvement that we made with Lily was to make the wavelength solution's functional form more flexible by changing from that 9th degree polynomial to an interpolation that's a non-parametric localized interpolation. Basically, we can afford to have more flexibility in the model, so we should do that. And we were able to drastically reduce not only the level of the residuals, but also the structure in those residuals by just making a change in the functional form of the wavelength solution. But we also realized that we have even more information or more power in the data than the density of LFC lines. Not only do we have a ton of lines in any individual exposure, we also have many, many calibration exposures over time. So Express now, and any instrument with such calibration data, now has stacks and stacks on calibration data across time. So we asked, can we use these this historical archive of calibrations in a hierarchical way to construct wavelength solutions that are informed by all of the calibration frames and not just the absolute nearest ones in time? In order to construct this sort of model, I want to take a little bit of a step back and think about what the fundamental assumption that we're making here is. That assumption is that we can do a dimensionality reduction model because we're saying that the spectrograph has a limited number of effective vectors along which the system can move. So like in how Game of the Year, Legend of Zelda Tears of the Kingdom, Link has the ability to pick up an object and you can manipulate it into any possible orientation in space using just these two vectors of control. That's a simple example of a limited number of basis vectors that can that you can project onto to achieve any different configuration. In the metaphor here, the spectrograph is residing in some kind of complex calibration state, but we can find a few vectors onto which we can rotate or move the spectrograph to represent any possible calibration position at the given time. And critically here, we don't need to have a full forward model to solve absolutely everything that can change in the spectrograph. The spectrograph's calibration state can remain a latent process that we're never directly modeling and inferring. What we want to infer is the projection of that calibration state onto the observable things. So we could think of it as inferring sort of the correct axes along which to manipulate the spectrograph in order to get in order to explain the observable wavelength calibration state. And we're getting those vectors by doing dimensionality reduction in the form of principal component analysis. So if we run PCA on the stack of calibrations across time, we come up with these basis states or basis vectors, which are actually 2D images here of wavelength, of LFC line positions as a function of pixel X and pixel Y on the detector. And we find that there are indeed a limited number of basis states here that contain most of the possible variants of the wavelength solution. So there's a limited set of significant ways in which the LFC lines can get distorted as the spectrograph changes. And we've come up with an efficient way of representing that through these PCA vectors. Now, all we need to do is say for any given time, we can represent the calibration state of the spectrograph there by the weights of those vectors to describe the current calibration. And we can interpolate between them to find what the calibration state should be at any given intermediate time, giving us a way to get a wavelength solution for any time, not just the times at which we took a calibration. I'm showing here the time series of the two strongest PCA amplitudes that describe most of the variance. And while PCA is famously uninterpretable, and we didn't construct this model to have a physical interpretation, we can actually afterwards point to some possible interpretations. We noticed in particular that the amplitude of the first basis vector strongly covaries with the optical bench temperature. And similarly, other bits of engineering data can tell us things about how the spectrograph is changing. So I think there's still work that could be done here in terms of incorporating better the engineering data that's taken to get a more complete and interpretable picture of the spectrograph calibration state, which might be a fun future project. But in the meantime, we have this very data-driven way, and this is a nice view of the whole process made by Lily for the paper. So just to recap, with any given LFC frame, we're able to denoise it using this dimensionality reduction to kind of inform it with all of the other possible wavelength solutions that have been observed. We can come up with this like latent space of spectrograph calibration states that's described by the basis vectors for wavelength solutions. And now all we need to do is locate any particular vector within the calibration space and interpolate to get the full denoised wavelength model. So we implemented this for the EXPRESspectrograph, and we found that we were able to improve the radial velocity precision significantly. So for this standard star, we were able to go down from 1.2-ish meters per second to close to 1 meter per second. And this is actually equivalent to removing 0.5 meter per second in the RV error budget, if you assume that the wavelength solution error is being added in quadrature with other sources of error here. And so this is now in use in the Express pipeline and seems to be doing a good job. So I like this example of the Excalibur method for Express because I think it is an illustration of how we can treat things as we can treat systems that we don't fully understand or aren't fully feasible to forward model, like the extremely complex state of the spectrograph's inner workings, as a latent variable and engineer it so that the data that we have tell us the important things about the spectrograph without needing to fully forward model everything that's going into it. So let's turn to a completely different challenge that we face. Once we have radial velocities with our excellent wavelength solution, how do we go about modeling them? And I'm making this transition here because the star itself is also something that is an extremely complex system where we don't fully know how to forward model it. So you can maybe see where I'm going here. But essentially, in order to do the forward modeling of the radial velocities, we want to be able to fit a Keplerian or a sum of Keplerians plus everything else that's happening in the time series. But a lot is happening in the time series. As you all know, the stars are changing in many different ways on many time scales. So I like this visual of the sun across its activity cycle, but of course, which is like very dramatic. But of course, there are also changes on shorter scales, including the rotation, convective overturn and granulation, and oscillations. And all of these things enter into the spectra that we see. So as the stars change over time, so do their spectra, and so do their radial velocities as a result. That means that stellar variability can be the big, bad, scary enemy that's opposing our models in a lot of cases. So how do we fight this with the data? I want to bring it back to that idea of the spectrograph or any complex physical system as a latent process for which we need to find the right projections to represent what's happening in the data space. How would we go about doing that if we think of the star itself as the latent system? What's the basis in which we want to work? So one answer to this is treat the star as a latent Gaussian process and constrain that Gaussian process using the time series observables that we have. This is a really excellent framework that was introduced in Vinesh Rajpal's 2015 paper, where he lays out the math for assuming that there's an underlying stochastic activity process in observing an active star. You can represent it by a Gaussian process. And while that Gaussian process isn't directly observed itself, it remains latent. Functions of that GP determine all of the different time series observables. And if we can jointly constrain the GP from all of these things, then we have the best chance at being able to isolate the latent, the stellar activity state and separate that out from the radial velocities due to a planet that we're interested in. Recently, I was part of this really fun project with Quang Tran and Dan Foreman-Mackey, where we decided to make a similar sort of framework inspired by Vinesh's to robustly model photometry and radial velocities jointly using that latent Gaussian process. So there's this FF prime method introduced by Susanna Grain that gives you a quantitative prediction for how both the flux and the radial velocities should depend on each other. And Vinesh pointed out how you can represent them as a Gaussian process. There's one problem or a couple of problems in directly implementing the FF prime prediction. One is that in this framework, the flux becomes the square root of the Gaussian process that determines the radial velocity. And that's not really possible to take the square root of the Gaussian process when we're trying to optimize this. Instead, we're a little better off if we treat the flux and the square of the flux as independent Gaussian processes, because the square root of a GP is a GP by definition. So the other issue that we have here is that the FF prime method works for one rotating spot. And we were interested in Quang's project in looking at extremely active stars that are going to have multiple spots that are evolving over a relatively short time scale, where we need a little bit more flexibility in the model than FF prime can predict. So as a result, we came up with this, what we're calling a two latent GP model. The name pretty much describes it. We describe both the flux and the radial velocity as linear combinations of two latent GPs, little f and little g here, and their derivatives. Notice that this formulation can turn into the FF prime formulation exactly if you assume that little f is big F flux and little g is flux squared. But it's got a little extra flexibility built in there. So how did we assess whether or not this is a good model? Quang simulated time series spectra and photometry using Rodrigo Luger's starry code for a very young, very spot-dominated star. So notice that these are very large radial velocity amplitudes. That's because we were working on this in order to apply to Kwong's Igrins survey of very young stars where the RV amplitudes are this big. We simulated data given realistically large and evolving spots. And Kwong generated a flux time series that's reasonable for a Kepler or TESS-like cadence, and generated a ton of radial velocities. So we generated many, many, many RVs, but we chose only a small subset, which are represented as the stars marked training RVs here, to actually train our model on. So this is equivalent to just observing at where the stars are. The reason that we generated so many RVs here is to use them as the independent validation or test set of the Gaussian process model. So essentially, this is addressing the possibility of the model overfitting by giving it lots and lots of chances to predict radial velocities where we know what the true answer should be and see if the model gets it right. We applied a bunch of different models to these simulated time series. One of them was using a single Gaussian process directly, using a single Gaussian process and serially training it by constraining the hyperparameters from the RV, from the flux, and then applying to the RVs, or using latent Gaussian processes, either one or two. And we directly compared for this case to the FF prime predictions because we were able to generate perfect flux and flux derivative time series. So probably the easiest way to compare these things is to look at the residual RMS in the RVs. And we did this by looking at the posteriors for these, sampling many different realizations of that GP model and looking at how the RMS changes across the region of possible fits. So what we find is that the two latent GP model that Kwong developed outperforms other models pretty significantly. It even slightly outperforms the FF prime model, which we think makes sense given that this is a very complex noise case with the evolving spots where FF prime shouldn't necessarily work perfectly. We also find that we get a similar degree of outperformance for the two latent GP model if we make the RVs and the flux asynchronous, at which point FF prime isn't even possible. And Kwong, this has been published, you can find it on arXiv, and Kwong is now working on applying this method to real data using his data sets of the young stars observed with Igrins. So this was a fun project where by adding a little bit of extra flexibility to our models in a somewhat physically motivated way based on the FF prime expectations, we were able to take advantage of the large amount of photometry that we might have for some systems and improve our ability to constrain the radial velocities. So that's cool. But what if we don't have photometry? How do we best make use of the spectra that we have in hand? For the last little bit of my talk, I want to turn to the piece of the puzzle of addressing variability of the star at the full spectrum level. And the motivation for this is that we know that stellar activity affects every part of the stellar spectrum. To illustrate, this is just plotting some bits of the two Wallace et al. Kitt Peak solar atlases taken for the quiet sun and within a spot on the sun. These atlases reveal that the spot spectrum is fundamentally different from the quiet star spectrum everywhere, even in the places that you wouldn't necessarily select as information rich for radial velocity use or would highlight as a classical activity indicator. This suggests that there's a lot more power in the data than we're currently making use of to diagnose stellar variability and spots. So how do we go about making use of that? This is, again, work with Lily Zhao and David Hogg here at CCA. So we decided to think about looking at the spectrum as a combination of spectra, a combination of components that are determining them. In particular, we're going to take as our data the time series for every single pixel or wavelength bin in the spectrum and say that they're all the observables. We want to look for a latent process that can describe their changes, and we believe that the latent process should be something low dimensional because of this picture that we have in our heads about the limited number of ways that the stellar spectrum can change. In particular, we have this prediction that in general, we have one spectrum from the quiet star. We have another spectrum that emerges from the spot. And that spot spectrum can be rotated to move it in one dimension. But some linear combination of these things ought to describe the net spectrum that we are getting at the end of the day. So to put this to the test, I'll walk you through the procedure here using these cartoons that Lily made that are very beautiful. First, we generate some fake data. So using Starry, we forward model a set of spectra where we've assigned a different spectrum to within the spot versus within the quiet star. And we can see that if we try to straight up measure the radial velocity from these spectra at different times, it's changing in somewhat complicated ways as a function of the rotation phase. Now, what do we do with these time series spectra? We want to come up with a small number of basis vectors to describe how the stellar spectrum can change. We need that representation of stellar variability in a low dimensional way. So there's a few different ways, well, there's many different ways that we could choose what these basis vectors are. And we've experimented with a few different approaches. So one option would be analogous to some of the stuff I was talking about in wavelength calibration. We could do PCA or some other dimensionality reducing technique on the data itself, using some subset of the data so that we can properly test with the left out validation data. So we could construct our basis vectors of the spectrum using PCA. Which would be probably the most data-driven option here. Another option would be to get a little bit more theory-driven. We could construct vectors here based on our physical expectations by doing things like, in this example of the cartoon, we would take a theoretically motivated spot spectrum or the Wallace Atlas and calculate the difference between that spectrum and the quiet spectrum and the difference between that spectrum and Doppler shifted and the quiet spectrum and take those as our basis vectors. We could even do things like taking the difference of the spectrum with respect to the stellar temperature, perhaps, or one of the other fundamental stellar parameters that we think is physically changing about the star. So there's a lot of different options here, and we're still experimenting with what the best basis vectors to choose are. But once we have those basis vectors, it's pretty straightforward what we do next. We need to project the spectra onto the basis vectors. So figure out at each time what fraction of each basis is represented in the observation. Doing that projection allows us to come up with a a contour where you can locate the spectrum at any given time or phase within this sort of latent space of the basis vectors. In this example, the location within this latent space along the contour actually tells us everything that we need to know about the latent system of the star. And you can see that it uniquely maps to different stellar rotation phases, depending on the location here. Once we're able to come up with this projection, all we need to do is basically treat that position in the contour as an activity state, or use the projections as new activity indicators. And then we can subtract those off from the radial velocities, or jointly model those indicators and a Keplerian model in order to get corrected radial velocities. So this is a pretty simplified version of the model using this mockup, but it does quite well in our tests and is even able to preserve a planet signal in the face of this. So again, this is all work in progress, but it has a lot of similarities to some published efforts already, including the DC-PCA approach, which is probably the closest to this, although they take the extra step of requiring that the basis vectors are all orthogonal to the Doppler shift vector. There's also been really interesting work by Michael Cretinier and Christian Gilbertson, who talked about this a bit in last month's colloquium, if you check out the recording. So I think that this is a general direction of data-driven full spectral variability models that seems to be really fruitful and is getting quite a bit of attention in the field. So I'm really interested to see how this all moves forward. But I think that there's a lot of promise in this picture of the star as a latent system, where we're trying to constrain how it maps into the observables without necessarily needing to solve from first principles everything that's happening in the star. Looking forward, stellar variability is a tough enemy, but we have the power of data on our side. And the question for the future is, who will win between these two? I haven't yet beaten the video game, so I can't tell you the answer. But I have hope that we will be able to use the data in hand as a really key weapon in the path forward to getting these extreme precision radial velocities and Earth detections. So wrapping up a little bit early, I guess, main takeaways that I wanted to communicate here. We have a really large volume of data in hand, and we're going to be getting even more with future extreme precision radial velocity surveys, including the Terra hunting experiment and others. This amount of data gives us a lot of power and opportunities. I think that we stand to gain quite a bit by taking advantage of this volume of data and making our models a little bit more flexible and a little bit more data-driven. But I still think it's extremely important to keep in mind interpretability and building our models out of our physical expectations and our picture of the system as much as possible. So I look forward to seeing continued work along this front from lots of people in this group. I hope this was a useful way of thinking about things for you. And I would be very happy to take any questions or talk further about stuff. Thank you.
Thank you so much for a wonderful talk and a great overview of this and many other similar works. So I invite folks to use the little clapping hands emojis if you want to show appreciation for Megan's lovely presentation, and then we'll open the floor up for questions. Please feel free to use the raise hand feature. Nathan, go right ahead.
Hi, Megan. Great talk. Thank you. So in a recent work with Jean-Baptiste Delille, we explored the opposite way, which is the model-driven approach to model stellar activity. And so what we thought about the FF prime approximation is that it seems to break down when you have limb darkening first, and second, when you take into account like the fact that the RV is affected by the shape of the line. But so I was curious, what are exactly the reasons in your mind which could break the FF prime approximation, and why would you need this additional process?
Yeah, good point. So yeah, so as you point out, there are some things like limb darkening which cause the FF prime method to break. But I think in addition, fundamentally, the FF prime method is based on one single spot. If you add in multiple spots, that's an additive effect in the fluxes, but it's not an additive effect in the FF prime. I don't have the math right in front of me, but I think based both on tests where we inserted multiple spots in the system and plotted the FF prime using Starry and saw that it's different, and also based on that sort of intuition about like the non-commutative addition there, I think that FF prime doesn't work great for multiple spots that where like it's not just one that dominates on the surface.
Yeah, okay. Thanks.
I've got a question in the chat, and then I'll come back to you, David. So Reggie in the chat says, can we use spectral regions other than the optical or the infrared to model stellar activity? So maybe via like ancillary data taken with other instruments, but on a similar timescale to your RVs.
Mm-hmm. Yeah, I think in general, increasing the wavelength range over which we have data is increasing the power that we have to model this. We see that for the sun, different forms of stellar variability show up extremely differently in different wavelength regions. I think the way that we take that into account might look something similar to the work that I was showing with Kwong, treating it as sort of one latent, perhaps Gaussian process that gets constrained by different data streams simultaneously. But I mean, it depends a lot on the details of what the data that we have at hand are exactly. But in general, yes, I think that moving to other wavelength regions can potentially give us a lot of power over some forms of stellar variability.
Okay, David Charity, you're up.
Hey, Megan, that was a really nice talk, and the work you guys do is really great. My question is more generic, but I'm always left with, in all of these talks and all of these different techniques, left with like a lack of understanding of how you're assessing how these techniques are eating into the Keplerian radial velocity signals that you're actually after. How do you make that assessment in a realistic way on real stars?
Yeah, that's a really key question. Obviously, in general, when you increase model flexibility, you're always running the risk of overfitting, and particularly, overfitting in pernicious ways that gets rid of the planet signals. So that's a super important question to address. I think there are principal tests that you can do that we try to carry out. One is to leave out some of the data and use that as an independent validation, which doesn't directly address the Keplerian or the Doppler shift signal, but does allow you to diagnose overfitting in general, which should help with anything there. So for the example of what we did in Kwong's project, generating lots of data that we did not give to the model and testing that way, was useful. If you had actual data sets and you weren't able to just generate all of the data for validation that you want, you might play some tricks with like leave one out validation, for example, where you train your whole model on every data point except for one and see how well it predicts that model, and then redo that for each possible subset. So there are ways to do this sort of validation of the models to diagnose overfitting. The other important thing, I think, is just to, as we did with Lily's work, back, if I can get this to go back. Why does PowerPoint want to access my camera? Right, we actually injected a Keplerian signal, and that was part of the testing suite. The last part of the question was, you mentioned for real stars, and none of this is real star data, but I think that in that case, the solar data can be extremely useful, and it's fundamentally hard because we don't know what the real planet signals are for any stars but the sun. So we got to rely on that, I think.
Yeah. Well, thanks. And I didn't mean to disparage the work. The work you're doing is great. I just don't quite understand. At the end of the day, we want to make, we really want to make an assessment as to the quality of the results that we get out, and we see, we've seen changes in that over the decades, right? As people have revisited the same planets that were discovered 20 years ago. And so I was just curious how you made that assessment. So thank you.
Yeah, no, I think it's a really important point to discuss, and very, most of the work of developing these new models is testing them in rigorous ways. So I think it's an important discussion to have.
Okay, next up, Gully, I see your hand. Go right ahead.
Hi, yeah, cool talk, Meg. Question is about Wobbly. So so maybe a few questions surrounding that. Do you view these sort of augmentations you're describing for the stellar activity as sort of living within like a Wobbly-like framework? And then next part of that would be, to what extent could you fit simultaneously, as Wobbly currently does, the stellar jitter part in this sort of interpretable way that you described, but also the tellurics, which may also have their own sort of physical variation that may or may not be predictable depending on what sort of restrictions you put on it. So I guess yeah, to what extent you've thought about that, how you think about that, and whether that could live inside of Wobbly or something similar.
Yeah, thanks. That's a great question and a great point. I think, yes, ideally, if this work is successful and we're able to come up with the right set of sort of basis vectors to describe stellar variability, I think the most robust way of applying that would be to directly forward model the full spectrum as the Wobbly model of spectrum times Doppler shift, and added to that some combination of these basis vectors, and it's actually currently possible in the implementation of Wobbly, because we built that in order to have data-driven telluric variability models where we actually learn what the right basis vectors are for the tellurics and what the weights are at any given time. I haven't been brave enough to just like try that with Wobbly for the star, because it's harder than the tellurics in that you need, I feel like you need so much more data in order to really disentangle the Keplerian or the Doppler shift signal from the variability signal, which can look extremely similar to the Doppler shift signal. And I possibly doing like giant Wobbly with variability on the star for the solar data would be a good way to go, but I haven't tried it yet. If anyone else wants to try it, I would be keen to hear what happens. And yeah, I think also your point about simultaneously modeling with the tellurics, that may well be necessary, especially as tellurics become more prevalent in the infrared. I think one of the drawbacks or cautions to taking this full spectrum approach is that you really need to understand all of the things that go into generating the full spectrum, which includes tellurics. And one of the benefits of some of the similar work that's been done in the cross correlation function is that you've gotten rid of a bunch of those kinds of complicating factors, or you've minimized them at least. So as we move to the full spectrum, I think we stand to gain a lot in terms of all of this, looking back at this picture, all of this information that gets thrown away when you just select a few lines and you calculate a cross correlation function. By going back to this space, you can gain a lot, but you also very much need to be aware of the tellurics and things that are complicating the picture. And so we need to be cautious about that and ideally model them all at the same time.
Okay, Nathan, is that a residual hand or you got a second question for Megan? Oh.
This was a residual hand, but actually I do have another question.
There we go.
Yeah, I was wondering if the results, so when you compare the different GPs, if the results change, if you change the autocorrelation function, if you change the kernel.
Yeah, which results?
So when you compare when you compare the FF prime method and the other one, I assume that you select a certain kernel, and I'm wondering if the results change if you have another kernel.
Well, we tested. Now I'm forgetting which kernels exactly we tested. So the version in the paper is the Matern 5 has kernel. We tested at least Matern 3 has. We might have tested quasi-periodic too. I don't know. I need to check my own paper. But we did do some tests with other kernels and didn't see a huge difference there. I don't really have a great sense expectations wise, whether it should change with kernel here. But it would be something to investigate more. But based on the initial tests, it looks pretty independent of exact kernel choice.
Okay, thanks.
I also wanted to say, I forgot to say in response to Gully's question that the question of simultaneously modeling stellar spectrum and tellurics is something that Kristen Gilbertson has been working on really and doing great work on that. So again, their colloquia from last month would be great to check out too.
Yeah, that is posted in our presentation archive for anyone who was not able to catch it in real time. Okay, any last questions for Megan as we approach the top of the hour? If not, let's thank Megan again for a wonderful presentation and a great overview of the work that's being done here. I'll remind folks again that our next presentation will take place on June 22nd and feature Dr. Connor Frederick. And so I hope to see you all there. You'll get reminder emails as we get closer. But for now, thank you again, Megan. Thank you everyone for calling in. And I hope you all have a lovely rest of your Thursday.